These are the answers to homework 5D. Here are the definitions I would like you to know. And now let's go to the questions. Number 1, determine the pressure of dry hydrogen gas collected in each of the following udiometers. Assume an atmospheric pressure of 756.0 torr and a temperature of 22.0 degrees Celsius. Water vapor pressure at 22.0 degrees Celsius is 19.8 torr. Our first udiometer on the left is one in which the hydrogen gas is collected by displacement of mercury. Because the levels of mercury inside the udiometer are the exact same as the level of mercury in the open beaker, that means that the pressure in the udiometer is exactly equal to the atmospheric pressure because both gases are pushing their level of mercury down exactly the same. So we would say, therefore, that the pressure of the gas inside the udiometer is 756.0 torr. In the second udiometer, the level of mercury is 231 millimeters higher inside the udiometer. That means that our hydrogen gas is only pushing its mercury down to here, where the atmosphere is pushing the mercury all the way down to here. Because the atmosphere is pushing its level of mercury down much further than the gas's pressure must be less than atmospheric. And because 756.0 torr atmospheric pressure is the same thing as 756.0 millimeters of mercury, we can directly subtract the 231 millimeters of mercury from the 756.0 millimeters of mercury, giving us a pressure of the hydrogen gas in the udiometer of 525 millimeters of mercury, or 525 torr. In C, we have the hydrogen gas collected by water displacement. Once again, the levels of liquid are equal inside the udiometer as in the open beaker. That means the pressure in the udiometer is exactly equal to the pressure of the atmosphere, which is 756.0 torr. However, when a gas is collected by water displacement, some of the liquid water evaporates into water vapor into the udiometer, and it's accounting for some of the pressure. So some of the 756.0 torr's worth of pressure in the udiometer is due to the water vapor. It was given at 22 degrees Celsius, the water vapor pressure is 19.8 torr. So if we subtract out the amount of pressure due to the water vapor, the remainder will be the pressure of the hydrogen gas, which is termed dry hydrogen gas pressure, and that comes out 736.2 torr. In the last udiometer, the level of water is 231 millimeters higher inside the udiometer than in the open beaker. That means the pressure of the gas in the udiometer is less than the atmospheric pressure, and it's less by 231 millimeters of water. So if the atmospheric pressure is 756.0 millimeters of mercury, we would have to subtract the difference in levels if it were millimeters of mercury. So we take the 231 millimeters of water, divide it by 13.6, and that would tell us what the difference in levels would be if it was mercury instead of water, and we subtract that from 756.0. Additionally, the water has evaporated into the udiometer, so some of the pressure in the udiometer is due to water vapor, and so that must be subtracted also. So making both corrections, the pressure of the dry hydrogen gas is going to be 756.0 millimeters of mercury, minus the difference in levels divided by 13.6 to convert it into millimeters of mercury, minus the water vapor pressure of 19.8 millimeters of mercury or torr, and that will give us the pressure of a dry hydrogen gas of 719.2 millimeters of mercury, which is exactly equal to 719.2 torr. Question number 2. Acetylene gas and calcium hydroxide are produced when solid calcium carbide reacts with water. From a sample containing calcium carbide, 2.18 liters of acetylene gas are collected over water in a udiometer. The water level inside the udiometer is 87.5 millimeters higher than on the outside. The water temperature is 21.5 degrees Celsius. The atmospheric pressure is 758.7 torr, and the water vapor pressure at 21.5 degrees Celsius is 19.2 torr. A. Calculate the mass of the calcium carbide that reacted. So we were given the reactants, calcium carbide and water, CaC2 plus H2O, and the products, acetylene and calcium hydroxide, C2H2 and CaOH taken twice. The reaction's not balanced. If you think of water as hydrogen hydroxide, there are two hydroxides on the right. We'll need a 2 in front of the water. and that actually balances the hydrogens, and the carbons and the calciums were balanced as well. To set up our stoichiometric calculation, we're given 2.18 liters of acetylene gas were collected. The question is how many grams of calcium carbide must have reacted to produce that, and the mole ratio on the balanced equation is 1:1. First step, convert the given information into moles. And because this is a gas volume, we're going to convert it into moles with PV equals nRT. The volume of the gas is 2.18 liters. The temperature of the gas is going to be assumed to be the temperature of the water, which is 21.5. But the pressure of the gas is not given, and we're going to have to determine it from the picture of what they described. The gas was collected in a eudiometer with the level of water 87.5 millimeters higher on the inside than the outside. That means the pressure in the eudiometer is less than atmospheric pressure. So to calculate the pressure of the dry acetylene gas, we take atmospheric pressure, subtract the difference in levels of water divided by 13.6 to convert it into millimeters of mercury, and then subtract the pressure of the water vapor that is evaporated into the eudiometer, and this comes out 733.1 or 733.07 millimeters of mercury with a guard digit. Now we know the volume, the temperature, and the pressure of the acetylene gas, so we can solve for the number of moles of acetylene gas with the ideal gas law equation. Converting the 733.1 millimeters of mercury into atmospheres, it becomes 0.96457 atmospheres, the volume 2.18 liters, the universal gas constant, and then the temperature switched to Kelvin, 294.7. Atmospheres, liters, and Kelvin cancel out. The moles in the denominator under the fraction bar flip to the top, and we now calculate the number of acetylene gas as 0.0869 guard digit 5. Once you have the moles of one of the reactants or products in any chemical reaction, you can now convert it to moles of any other reactant or product with the mole ratio and the balanced equation between the two substances. In this case, the mole ratio is 1:1. We put the acetylene on the bottom and the calcium carbide on the top, so the moles of acetylene cancel out. And the third step is to convert this into the units of the answer. They want the answer in grams, so we will use calcium carbide's molar mass to convert the moles into grams. And the final answer comes out 5.57 grams of calcium carbide must have been in that sample. Part B, if the sample was known to be 90.0% calcium carbide by mass, calculate the mass of the sample that reacted. So in Part A, we calculated that if you're going to produce 2.18 liters of acetylene, you have to have 5.57 grams of calcium carbide to do that. However, they said that the sample was 90.0% calcium carbide. So this is an equality statement. If you have 100% of a sample, it's 90.0% calcium carbide, and they said that was by mass, which means I can now put units on these numbers. I can say 100 grams of a sample must contain 90.0 grams of calcium carbide. And now I have a conversion factor between calcium carbide and the sample mass. So if we need 5.57 grams of calcium carbide, I'm going to multiply by this equality statement. The calcium carbide has to go on the bottom to cancel out. The sample goes on the top. And now we'll convert this into how many grams of the sample must weigh. That comes out 6.19 grams. See if that makes sense. You need 6.19 grams of the sample to ensure that it has the required 5.57 grams of calcium carbide. Problem number 3, calculate the root mean square velocity of nitrogen molecules at two different temperatures. A is at 273 Kelvin. So to calculate the root mean square velocity of any gas molecules, we use the Vroom's equation. The root mean square velocity equals radical 3RT over the molar mass. The molar mass will be for diatomic nitrogen, and the R value will have to be the one that has units of kilograms meters per squared per second squared mole Kelvin. So in the numerator, it's 3 multiplied by 8.314 kilogram meter squared per second squared mole Kelvin, multiplied by the temperature they required, 273, and we have to divide by the molar mass of diatomic nitrogen, but it can't be 28.02 grams per mole, otherwise the units wouldn't cancel out. So I had to divide that by 1,000 to make it kilograms per mole, and that comes out 0.02802 kilograms per mole. Now the kilograms cancel out, the moles cancel out, the Kelvin cancel out. So our units are meters squared per second squared, but once I take the square root of the entire parentheses, then the units get square rooted as well, and it'll come out meters per second, and I get 493 meters per second. In part B, you do the exact same calculation, just the temperature is now 546, and if you did that correctly, you would have gotten 697 meters per second. Question 4, graph the relative number of nitrogen molecules versus their velocities at these two temperatures. So when you have a group of molecules, they're gaseous molecules at a particular temperature, they will have a range of velocities. And so if we graph the velocities on the x-axis, there'll be molecules with low velocities, there'll be molecules with high velocities, but they will all center around an average velocity, which is 493 meters per second. If we raise the temperature to 546, the root mean square velocity, the average velocity we just talked about, is going to increase. In fact, it's going to increase up to 697. So as it increases, this curve, instead of just completely shifting over, spreads out so that the average now is at our higher velocity of 697. But notice the curve is flattened because the molecules are spreading out over a wider range of velocities. The area under both these curves is identical, which means the number of molecules in the container are the same, but the graph is actually more spread out as the temperature increases because the molecules not only have higher kinetic energies, but they will still have a number of molecules with low kinetic energies and therefore low velocities as well.